The variance for a random variable is just a metric to use to see how much spread I might expect to see once I take a sample of observations. So this is a little bit similar to the mean of a random variable in that I don't expect that my sample will have a mean exactly the same as my random variable's mean. It's just that once I take a huge amount of observations, I expect the mean for that to be very close to what my variable's mean is. It'll be the same here, where I don't expect the variance in my sample to match up exactly with what I have for my expected variance that I'm about to show. It's that when I take a huge amount of observations, I will expect the variance to be very close to what my variable's variance will be. Now, the calculations for this are a lot more involved and tedious than for the mean, so I'm not really going to have us do this, but this is basically what it looks like. This variance for a variable is the expected value of how far apart an observation is going to be from the mean squared, right? Because remember, that was the issue with the variance, and why we tend to want to work with standard deviations is I've got this kind of square in here. Well, I can use this alternate version for calculations. This variance is actually the expected value of my observation squared minus the mean squared. So I can do all this calculation. So what I need to do, much like the table that I made to make the mean calculation, instead of finding the expected value for a single observation by itself, I'm finding the expected value for that observation squared, which sounds odd, and it honestly kind of is, right? So I'm going to take all my y values and square them. So this is all of my possible y values squared, like the same PMF table as I used for the mean. And then I'm going to multiply all those squared y values times the probability of it occurring. So for example, this 2.88 here is 16 times 0.18, right? So my y is 4, I square that and multiply it by its probability of occurring. After I calculate all those, I need to add that up to get this 9.84. So that's the first part of the formula. And then, of course, I would have needed to calculate the mean. Luckily, I already did that in the previous video. So I could take that 9.84, subtract off the mean that we calculated squared, and then I finally get my answer. And realistically, I'm probably going to be more interested in standard deviation, so then I need to take the square root of that. Now, if I hadn't already put in all these calculations and already done the mean in the previous video, this would be a 20-minute long video. It would be extremely tedious, and this is with only 6 possible outcomes. Once I start doing this for the number of customers that a grocery store sees, like we're not going to do that, right? That would be an insanely tedious set of calculations, or all the different other things that we'll be doing in this course. I don't want us to do that, so I'm going to leave it as expecting you to be able to calculate a mean because it's fairly straightforward and fairly quick, but we won't be calculating the variance, nor will I expect you to know the variance formula. Instead, I'll expect you to know how to interpret this thing. And realistically, it's the same as what we had before. Just we don't have data, so this is just where we expect a variance to be, but it's still a measure of spread. Right? Where 0 would mean we expect there to be no spread in the data at all. Everything's going to be the same value. And larger values for the variance means we expect more and more spread. And same idea for the standard deviation, right? Larger standard deviations are more spread. 0 is the smallest it could be, and that would mean we expect there to be no spread in the data. We're still in the world of probability, so we don't actually have any data. We're just saying what a sample would look like if we were to gather one. So as long as we keep that idea of what we expect to see rather than what we did see separated, right? The difference between a sample variance and a random variables variance separated, then realistically we've got everything we need for this topic.